Okay, so hello, this is the CUDAN Open Lab seminar on November 14, 2022. Today we have Armand Leroi from the Imperial College in London, from the Social and Cultural Analytics Lab. So you conspicuously named your lab in a similar way than we did, more or less dependent or independent in one way or another. Probably we were inspired by you, I guess. Or we were both inspired by Mathematics, or everybody was inspired by what was going on in 2016 at UCLA. So we are, very curious about what's going on in your place and what you do. This was officially or initially planned as a lab encounter, but I think it's a lecture, right? And so what we usually do in these kind of open lab seminars in lecture mode is we get 2 hours, and the sort of idea is to spend about 40 minutes in a talk, in presentation mode and about 80 minutes in discussion mode. But if you want to discuss, if you want to present for 2 hours, you're very, very welcome. If you want to take questions in between, you're welcome. If you say, I want to have questions at the end, you're welcome. So basically, the 2 hours are yours to sort of decide how you sort of like do the ceremony. And I would just hand over the stage to you, if that makes sense.
Thank you very much, Max. Everybody can hear me well?
Yes.
Good. Well, I decided to give a little bit more of a lecture mode because I wanted to tell you about some of the things that a variety of people have been doing over the last few years, and many of these people aren't. Some of these people aren't around anymore, and so on and so forth. So I'm delighted to be able to talk to you. That's especially because this kind of grouping, where we have people who are deeply interested in culture, but who are natural or computational scientists, is still a little bit unusual. I find that there's a wide open field here, and it's still relatively rare that I can find people who I'd like to talk to. So I'm delighted to be able to do so. Let me begin by giving you some background. Sorry, I've just got to share my screen here. Yeah, geez. There's the share screen.
I think you should be able to do so. Yes, okay.
Nice. Just got to move things around a little bit here so I can see my icons. And there we go. All right, that's good. I've called this talk the evolution of almost everything. I think maybe because we've got so much time, maybe we can break it. Just you know, if people want to jump in with questions, by all means do so as we go, because I'm going to be talking about a variety of different things, some of which will be familiar to you, some of which conceptually, some of which may be not. So I'm happy to sort of make this a little bit more loose than a normal lecture. Let me begin with just my own background. I'm an evolutionary biologist, and you may wonder why an evolutionary biologist is talking about culture. And the reason is simply because I believe, and this is not a unique belief, you will be familiar with this, that culture has something very, very much in common with organic life, namely that they evolve. And by that I mean is that at the thing that makes culture and organic life special is, first of all, its diversity. Now, this is a picture of some hummingbirds from the Natural History Museum. This is a picture of a famous British DJ, John Peel, his music collection, his LP collection, and a library of science, and all these things, music, scientific papers, and all this stuff, all this culture that we generate is incredibly diverse. And I think it happens by a process very much like it happens in organic evolution. And the reason for that is the reasoning behind that is very simple. It's that there is, I think, culture evolves by a modification by descent process, to use Darwin's words. So just as we can look at, fossil record, here's a fossil hummingbird versus a modern hummingbird, we can also look at the stuff that we make. I'm an evolutionary biologist, so I generate papers in evolutionary biology and put them in journals like Evolution. And those papers, their concepts can in turn be traced back to, as it were, our own common ancestor, The Origin of Species, which Darwin published in 1859. The idea is very simple, is that no thing that we do, no paper we make, no piece of art we make, no poem, no painting is ever generated de novo. It is always the consequence of taking something from somebody else, mixing it up, and possibly, although probably rather more rarely than we suppose, actually adding something original to it ourselves. When we want to do science, on whatever we're talking about, we need to phenotype, as biologists call it. And if I use some biological terms that you may not be familiar with, just do mention it. One of the so the thing that really motivates all my research is the fact that now, very much analogous to the genomics revolution in biology, we now have access to vast amounts of data, given that virtually all the cultural world has been digitized in one form or another. And it's not entirely true, but it's all rapidly being digitized. And the only question is then, how do we actually study that? And to that, we need to be able to study the features of the things. We need to, as a biology, call it phenotyping. Now, one of the techniques of phenotyping that I use quite a bit, have used, is something called topic analysis, which you would be familiar with. If you're a biologist, it turns out to be very similar to a method in genomics called structure, which is, they were invented roughly simultaneously, and both depend on latent trichle allocation. But I don't want to get into the technical details if you don't know about it. Let me just give you a feeling for what I'm talking about. It's usually used on text. And here I've taken 10,000 relatively new novels. I'm not going to be talking much about them. I'm just going to give an example. Things like these two books, these are just genre novels. There's a zombie novel on the left, and there's a typical romance novel on the right. And we take them, we look at the text, and we can identify topics that are specific to them. That is to say, groups of words that are co-associated in the document. In the case of The Walking Dead, it's world, dead, living, survival, apocalyptic, all these sort of words crop up. Then we can call this zombie slaughter, hot night, beautiful woman, billionaire, and so forth, crops up in another topic. And we can call that Take Me, You Bad Billionaire. Now, of course, the great thing about topic analysis is it's kind of a clustering algorithm, but it allows you to assign a probability that a given topic is found in any given document. So it's a kind of a soft clustering technique if you don't know about it, but we can talk about it if it's a well-known method. I'm not going to talk about novels here. What I want to talk about is actually the evolution of pop music, and this has already been published for some time, but it gives you a sense of what I'm interested in. So I became interested in the evolution of music, and at first I became interested in world music. The idea that people sing different ways in different parts of the world, and that one could analyze this and possibly recover the song. So I started collaborating with some music information retrieval people at Queen Mary University here in London, where they've got a Center for Digital Musicology, and they're very good on MIR, music information retrieval. These are all the kind of methods that you use to analyze pop music. And it turns out they are actually better for pop music. So the first project we decided to do is to study pop. And we got 17,000 pop songs, which are the hot 100, 1960 to 2010. We just basically were able to download them all, and we began phenotyping them. And I won't go too much into the details, but I'll just give you a sense of how it works. You take the audio and you extract various low-level features, such as harmony, and which gives you the chords. You can also extract things called MFCCs, which can tell you, if treated suitably, about the timbre, the kind of instruments, and other kinds of traits. And then you can discretize these and estimate the probability that these traits appear in any of your 17,000 songs. But what we found is that one of the best ways to deal with this is actually using, and this is a little bit unconventional, topic analysis. So it's not applying to text, but rather grouping these features with these discretized features into topics. And so we get a bunch of topics out the other end, which characterize these 17,000 songs. And now we can begin to do some science. We're inspired by the idea that you can look at the evolutionary dynamics of songs or things. And so a lot of our work is actually concerned with sort of time series, because evolutionary biologists love time series. The classic case is where you have in evolutionary biology is where evolutionary biologists have gone out and they've sat on some rock in, let's say, the Galapagos, and they have studied the evolution of finches, let's say, the beaks or the wings or so on, the body size of these things, and they've measured them year after year after year. And the reason they do so is in order to ask what kind of patterns of evolutionary change do we see and what can we infer about the processes? Well, that's the kind of thing that inspired us. And of course, paleontologists, when they look at the fossil record, they can do this over much longer periods of time, albeit with much lower resolution. So this is the kind of thing that we're interested in. And here, let me just show you what we do for pop music. I told you that we had the US Hot 100, 1960 to 2010. And you can take these topics, and this is one particular topic, and you can just ask people to describe them. And it turns out this particular topic on the left basically is guitar, loud, energetic. It picks up, well, what it picks up is this, da-na-na-na-na, basically. And what you're looking at here is the frequency of that topic in this population of pop songs over the course of 50 years or so, as it rises and falls and rises and falls and rises. And that is the rise and fall of rock and roll, essentially. And here's another topic, which is a curious one. So we have a chord measuring algorithm. And what this does is it looks at the distribution of the energy distribution across the notes, and attempts to infer a chord that is being played. And it's very good at doing that, but sometimes it just kind of throws up its hands and says, there's no chord here whatsoever. And what we find, curiously enough, is that there's an absence of chords. Nearly all music has chords early on in the 60s and 70s and 80s, but then suddenly the frequency of music, of songs that don't have chords begins to increase. And you may say, well, how can this be? What kind of music doesn't have chords? And the answer, of course, that it's rap. What you're looking there at is the rise of rap or hip hop, because that has a large component of spoken words. And when you hear a stretch of spoken words, the chord algorithm just basically throws up its hands and says, can't find a chord here. So that's the rise of hip hop. And so you can see the evolution of genres in this here. Now, one of the things we're interested in doing is characterizing these evolutionary dynamics in a more abstract kind of way, fitting models to it, and thereby inferring the kinds of forces that have been worked, that are kind of operating upon that from the patterns. And let me just introduce the kinds of patterns that we can look at. So the null hypothesis is that these traits evolve as a random walk. And that random walk can vary in speed and jump size to give you a fast or a slow random walk. But you can get other dynamics in there. So for instance, you can have a time at which there's a sudden, very rapid change in rate, and which we could call a revolution. Or you could have a random walk plus drift in which there's some sort of, in which you have a random walk, but there's a kind of a dynamic that is pushing it to one side. Or on the far left, on the far right, you can have a mean reverting process in which there's some force that is maintaining the frequency of that trait around some equilibrium rather than allowing it to travel out into random walk space. Now, you can characterize any given time series if you've got data good enough using various time series statistical methods as belonging to one of these things. And the idea is that we can infer something about the forces that are shaping it. The first thing I want to talk about is revolutions. Sorry, I'm just right. So the idea that there are revolutions over time is a very old one, and it crops up in many different aspects of science and history and so on. I mean, think of Kuhnian paradigms, for example, or just the casual way in which historians throw the notion of revolutions around. Of course, it appears in biology as well in the guise of the notion of punctuated equilibrium. You may know that punctuated equilibrium was proposed by Gingrich and Gould back in the 70s. It's the idea that evolution doesn't proceed by little steps, but it proceeds primarily by large jumps. And it is no accident that Steve Gould, now dead, famous American paleontologist, was a Marxist. So he was very much alive to the consequences of revolutionary change and looking for it in the fossil record. Anyway, I won't go into the whole paleontological controversy. I just want to say that this is part of what inspired us. And paleontologists have been dickering about this for ages, mostly because they don't actually have a terribly good way of measuring what constitutes a sudden rather than a gradual change. Never mind historians who of course really don't do quantitative analysis at all. Well, my friends and I, we thought we could do something better than this, and we developed what is a revolution detector. All right. So the revolution detector is simply this. It's a little algorithm which is based upon something called foot novelty, which comes from audio processing. It looks for sudden changes in a time series of some sort, something that you're measuring in the audio. But we're now applying it to time series of traits in music. So what you do is you have a whole bunch of traits which you've measured in your songs over various times, and you've got them, you group them by years, and you measure the distance between any time step and any other time step, all the other time steps ahead of it, essentially, right? So or all possible time steps. So you get a distance matrix, and that distance matrix then looks something like this. And you will see that this is a hypothetical distance matrix, this is from year to year to year to year, right? It's not between individual songs. And you will see that there are blocks of similarity over here and over here. And those blocks of similarity tell us that there's something very similar there. Those years are similar to each other in terms of their musical qualities. And that where you see there's a transition over here, there's something that's changed. Now, what we want to do is we want to quantify that, and I won't go into the technical details because it's been published. But what this revolution detector does is it runs along this diagonal and then estimates the amount of change at any given time point, and it can do so over either a very short period of time, because revolutions could happen very quickly, or could happen over a larger period of time. You can specify that, or you can study them all. And essentially what it's doing is it's measuring the rate of change at any given time point relative to the background rate, and you can do then, you can do a permutation test in order to identify when do you see times of change that are significantly higher in higher rate of change relative to the background change. And that is what we think is actually a revolution, a concrete quantitative notion of a revolution. And if we apply that kind of logic to and that algorithm to our pop music, and this was the punchline of the paper, we identified the revolutions in pop music, of which there were 3. I won't go into them all. I'll say there was 1964 turns out to be a revolution. Remember, this is the US Hot 100. So you can discuss what exactly you think that might be. Then there's 1982 is the center of a revolution. And then there's 1991, which is the center of a revolution. Remember, this is just the center of a revolution. What are these revolutions? Well, I'll tell you what this one is. It turns out that this is the biggest revolution in American popular music viewed from this data set. It turns out to be hip hop or rap. It's just completely different from anything else that comes along and has a more profound effect upon American popular music than anything before. You will note that the revolution, because we're talking about the Hot 100, right? So what's charting happens much later than the origin of hip hop, which the first serious song was Rapper's Delight, which was back in the 90s, which actually charted. But it was only until 1991 when Vanilla Ice, of all people, actually got the first #1 on the US Hot 100, coincident with our revolution. And by that time, I guess you could argue that it was all over.
Can I ask a question?
Yeah.
Let me just switch on everybody here. Yeah, so this is super interesting. And so the question is, there's different ways how to look at this, right? One is to sort of the genres that we anticipate, which in US American music are very much sort of like pre-given, right? So there's a kind of like Led Zeppelin is rock, it's not, but even though it may cluster together very similar with Bach, and then there is certain things where, would you find it in the R&B section or would you find it in the rock and roll section was often determined by the skin color of the person who actually performed as a leader. And so now one of the key questions is there's also the technological undercurrent, like, your first revolution also coincides with MIDI, and your second one arguably was the rise of the Akai sampler, meaning breakbeat. And if you would go further onward to 2007, for example, you find this auto-tune and compression thing. Obviously, you don't see that here because you have boundary effects in the data. But if you look at the spectrograms of the top songs, you actually find there's that kind of thing going on, that there's like every top 1 song looks the same in the last 10 years, basically, because they use the same compression algorithms. And so the key question is, in how much are the old categories coming out of musicology, out of experience, record store culture, how much are they in line with the data, and how much is the data actually sort of bound towards technology of music recording and the way it is produced? Is that something you could disambiguate, or do you think rap is like that one thing that sort of like is really different?
So there's 2 questions there. Let me see if I can answer the simple questions. Let me see if I can answer them. So our analysis is neutral with respect to genre, insofar that it doesn't depend upon it doesn't depend on anybody identifying what the genres are, right? It's just looking at the audio and clustering essentially in an unsupervised fashion. Now, we did get a whole bunch of tags from Last FM, a defunct streamer killed off by Spotify, I think. where people had tagged music with genres, and we mapped those tags to a classification that we then built on top of this, and we found that it mapped pretty well. But of course, people have all sorts of funny notions about how songs about what genres individual songs are, right? I mean, as you say, it's not very cut and dry. So that is then. What about now? Well, I don't talk about it now, but inspired by this, we haven't published this, but inspired by this paper, the BBC asked me to do a television program for the same thing, but on UK music. And we did this thing, and it was called The Secret Science of Pop. Why the secret science? I don't know, because that's just what TV producers do. Anyway, so we ran the same analysis for UK pop, and we ran it until much more recent data. I think this was through until 2017. And so I won't go into the details of the difference, the dynamics. I have to say, needless to say, rap isn't important in UK pop music as a revolution. It turns out that the analogous revolution is EDM, electronic dance music. That's what it's all about. At least that's the big change that happens. And what I think that to answer your question, what is true and what we detected is that the classical genres were breaking down over the last 10 years or so. And the reason for that is, we think, we had some music producers on this program, is simply because the musical world has essentially become much flatter as kids listen to everything and anything, and producers respond to that by mixing all sorts of stuff into songs. So genres are much less clear. I could continue with asking this. Your other question was about technological change. It's whenever we find a revolution, we have not attempted to identify what the cause of the revolution, whether it's technological driven or economically driven or whatever. There are many possible explanations. This is just fundamental to the difficulty of identifying the causes of unique historical events. It's a revolution. That's all I can say. But exactly what causes, I don't know. Mike Tan has a question.
Yes, basically, my question is basically as follows. As far as I understand, your result is significantly dependent on the set of topics you identify in your data set. Is it true?
No. So, for instance, we analyzed, we've looked at large numbers of different topics. We've set topics to 16 or 100 or 1,000, and the same result basically obtains.
Yeah, well, that I understand. Question number one: are topics, for example, in UK dataset and US dataset are the same, or are they different? Or if I split, for example, half of this dataset, will topics be the same or different?
So that's a good question. I don't know. And the reason is because I've analyzed each of those data sets as a unitary thing by themselves. I've never analyzed the UK and the US data together. And I've never attempted to split it. My guess is that almost certain is that some of the topics will correspond. They'll be picking out essentially the same qualities. In other cases, they won't. But that's hardly surprising because every corpus will naturally have its own properties, which the topic analysis will attempt to capture.
But then there is this, well, I'm not sure if it is a problem or not, but the question is, will these revolutions persist if I sort of embed this data set into a larger data set which will have a different set of topics? And will the fact that there is a revolution in 1990 survive aiding, I don't know, Chinese and that there is a revolution in American music in 1990 if I sort of have this American data set, then add British, German, Chinese, Korean, etc., and analyze the tropical structure altogether, and then ask the question about the American set.
Well, I have no idea, of course, right? I mean, I can make no claim. Well, I can make no claim for a global data set. I can only make a claim for the US. I mean, and as I suggested, if you do a similar analysis with the UK charts, you'll find that some things pop out the same, are similar. But as I said, the RAP revolution doesn't crop up in the UK where an EDM does. And it is perfectly conceivable that if you were to combine the data sets, that they would kind of cancel each other out and fail to give a revolution, right? But this is, I make no claim about global, changes here, right? Any other questions about POP? No? Let me just.
I have millions of questions, but I think we should go on.
What's that?
I said I got millions of questions, but we should go on.
Okay. Well, okay. So let me give you a sense of how, we've got time series, and I want to return to these evolutionary forces that are shaping it, right? Or these patterns that we can detect in these kind of time series. So I spoke about revolutions, but let's just forget about them for a bit. You can take those time series, individual time series, and you can ask, using various time series methods, you can classify them. You can ask, are they a random walk, right? Or are they mean reverting, right? These techniques come from econometrics, by the way. Because this is what people who analyze financial, changes in financial instruments do. It's terribly important for that as they attempt to predict what the markets are doing. And so you can ask if it's a random walk or it's mean reverting, and you can ask if that process is unbiased or biased. If it's got a directional thing or not. Now the one that's a little bit difficult to understand intuitively is the combination of mean reverting and biased. So the way to think about that is that essentially what you've got is you've got a process that is bouncing around some equilibrium, but that equilibrium itself is changing in some directional systematic fashion, right? So that there's a sort of shifting target along which these things are evolving. Anyway, you can classify your traits in your topics, frequencies of topics in this way, right? And then you can analyze them, and you can ask how many are random walks, how many are mean reverting, how many of them are biased versus unbiased. And the answer is that nothing in POP is a random walk. It turns out everything is mean reverting. And the only question is whether it's a biased mean reverting walk or an unbiased one. Let me give you sort of an intuitive sense of what I think is going on. So one of the most biased mean reverting topics we found is indeed topics associated with RAP, right? Aggressive speech, percussive, energetic. These are all descriptors which have come out of the data. When you ask people, what are they, we get people to listen to them, and I say, what are these topics, describe these topics. So this is RAP, and that it should be a biased topic, right? A biased time series is hardly surprising because RAP sort of rockets up in frequency from the 80s onwards, right? That it's mean reverting is a little bit more surprising because that suggests that there's some equilibrium around which it's bouncing in the charts at any given time. And let me give you just a sense of what I think is an intuitive sense. I can't prove this, but an intuitive sense of what I think is happening here. Bear in mind, this is the charts. So I think what is happening is that at any given time, there are, at any given time, the American record buying populace, they like to have a certain amount of RAP in their charts, right? But they like just the right amount, not too much, not too little. If there's too much, they begin punishing rap songs. They don't buy them. If there's too much, if there's too little, they tend to favor them, right? There's sort of a frequency-dependent force acting upon them, I suppose. But and this is, what I suggest is that what's happening is that equilibrium, that desired amount by the American record buying populace as a whole, changes over time, it's increased. And as it increases, that equilibrium shifts as people become more and more accustomed to rap, or as rap itself becomes more friendly. And I can give you sort of, I can give you a sense of how this kind of works, just in purely anecdotal, personal way. Back in the late 80s and 90s, I was in a lab, a fruit fly lab in Irvine, California, studying fruit flies. And we had a guy in the lab who was really into gangster rap. And he used to play this in the lab to our intense irritation all the time. And I found this music deeply alienating and really unmusical and horrible, and it was, and we finally managed to shut him down, because after all, it's a lab, right? You can't have people playing irritating music. Well, so that's the late 80s and 90s. Fast forward 20, 30 years, and there's a film that comes out. What is it called? Straight Outta Compton. And it's about the history of NWA, who in the meantime have become national treasures. And like every other middle-aged, middle-class white guy, I go and see it, and I'm just absolutely enthralled by the music. And I come out of there thinking, yeah, you know what? Fuck the police, right? And that tells you that is essentially one man's journey into gangster rap, right? It's a sense of how tastes change, and of course the music evolves, change, and I think that's essentially what's happening as when we go along here. What about an unbiased, mean-reverting topic? There's a topic, female voice, rounded, smooth, harmonic. This is associated with women singing ballads, essentially, and the fact that it's a mean-reverting topic tells you that there's some equilibrium force that is keeping it in the population at any given time. And what this just tells you is that there's, at any given time, regardless of over the last 50, 60 years, that there's been an appetite for women singing songs, typically about boys who've done them bad, and be it London Grammar or Adele or the Supremes or whatever. It's always been there, and there's just a continual appetite for it, which is keeping these topics at some frequency in the population. And the same is true for these topics over here, rock and roll, which essentially capture rock and roll in one form or another. And what this tells you is that, although rock and roll, I cannot say that it will never die. It has proven exceedingly hard to kill, because it seems that even though it rises and falls in frequency in the population, there seems to be some equilibrium force that is keeping it. And the kind of equilibrium force that we think is keeping it is very much, essentially, is frequency-dependent market forces, which are very much analogous to what maintain polymorphisms of snail colors in the population. I won't go into the details of this, but people have monitored snail colors over 50, 60 years, and it turns out these are genetic polymorphisms which predators just keep maintaining this variation in the population, as it were, each morph having its own particular niche. Yeah, Maximilian. Yeah.
Yeah, I got a question. Maybe I should switch on the camera. So this is all super fascinating. One thing which comes to mind, though, is that these rankings, and the Billboard charts are a ranked list. These rankings are logarithmic, right? So that it's not like that.
Oh yeah.
They're sort of like selling in sort of equal amounts, but the top one song is bought 100 times more frequent than the top 10 song, which is bought 10 times more frequent than the top 100 song. And so one of the interesting things is that the story you're telling of having a sort of frequency fitness, some kind of level around which you fluctuate, has an interesting property, namely that if you look at the individual item level, the fluctuation towards the top has a bound, while at the bottom, there's like, you can totally fluctuate to zero. So there's these fluctuating over orders of magnitude going on. And Financial Times series people have done this. We have done something in Physical Review Letters where we looked at a great number of systems. And one of the interesting things is that these systems are fundamentally unstable. So at the song level, this should be unstable and is, because stuff fluctuates in and then fluctuates out. What you're saying here is super interesting, namely that if you summarize sort of the story to sort of genres, meaning not just one rap song, but sort of all the songs of Grandmaster Flash or all the rap songs coming out of Def Jam Records, then you will actually have this sort of like mean reverting thing. There is an actual mean going on. And it seems like in your case, you don't get a kind of logarithmic kind of fluctuation, but you really get a fluctuation that sort of is within more tame regime, something one could indeed run a business on. So would this mean that it is dangerous for the individual artist, but really a safe thing for, say, somebody who runs a label or something? I'm sorry if the question is like, it's hard.
It's dangerous. All right, so you're absolutely right. So just to speak broadly, the songs change, but the music remains the same. That's basically the message, right? I would love to have the data of sales of individual songs, right? And the reason for that is because, as you suppose, it is a metric of fitness. I will speak in a few minutes about another data set, another context about fitness explicitly. Suffice to say, we don't have that data for songs. If we did, then we could do as evolutionary biologists do, and we could measure the intensity of selection directly upon these traits, as opposed to inferring it indirectly from the dynamics over time. Mm-hmm. Does that make sense?
Yes.
Yeah. All right.
Thank you.
I'll come back to this question of fitness in a different context later on. And if you have a data set in which you actually have sales as opposed to ranks, because we have tried this with ranks, but it's not adequate, presumably precisely for the reason that you adduced, namely that the ranks are logarithmic, essentially, right?
Yes. Yes.
Then we would be like, musical gods, right? Because we would really be able to tell you something about the forces shaping this in a much more direct fashion. All right.
One thing we learned maybe as an add-on is indeed, if you have score data, which we don't have for culture most of the time, but we have for plenty of other systems, then score stability is easier to achieve than rank stability for obvious reasons, because if you and I sell 19,000 CDs plus minus 200, we fluctuate around each other by rank, while we still sort of like on the same score, while rank 200, for example, in 1 year may mean 19,000, in the next year it might mean 50,000, I don't know, depending on like what the changes are. So this is a really interesting kind of field, and I thank you very much for introducing it that way with biology in the loop, because I think this topic is so fundamental. It's probably, one can neither solve it just looking at biology, nor just at financial theories, nor just at culture. We have to look at it as sort of like the fundamental pattern it is across systems. It's very Mandelbrot in a sense, right? Yeah, thank you very much. It's great.
And underpinning this, there are deep similarities between economic theory and evolutionary theory. I'm not enough of a mathematician to really cash them out, to be able to, a really clever mathematician would be able to actually really sort of cash these out and generate a unified theory which which would show the relationships between them. That's a slightly more abstract topic. All right, let me just move on to text, right? So again, we're still with topic analysis, right? I mean, it's quite a workhorse kind of way of phenotyping things, and as scientists, we were really interested in phenotyping. If we're interested in text, the most obvious thing that we might want to do is study the evolution of science, right? The science of science. That's what I want to turn to now. So we've done a couple of studies, but the first one I would just want to show you, just to give you a sense of the sort of thing you can do, is is we took 32,000 articles about conservation biology and ecology, and we did a topic analysis of them. And this is a map of ecology and conservation biology. You can do this with any discipline, but this happens to be this particular one, and it shows the kind of topics involved in. What we did in this paper was we just showed that about how this field has changed over time, how conservation biology turns out to become increasingly more a social science rather than a biological science, as people get more and more interested in the impact of humans on the environment. Here's another kind of study which we did, which is we got the BMJ, the British Medical Journal, Britain's premier journal, a medical journal, along with the Lancet, but this one happens to be free, and collaborating with a bunch of obstetricians in Amsterdam, women, they were fascinated by this data, and they wanted to know about women's health, right? So we wrote a paper about which we analyzed how well are women as subjects, medical subjects, this is not as doctors, represented in this data set over the course of, 75 years or whatever, whenever the data are good. Maximum, did you have another question? Your other duties up. Okay. Well, here's the bottom line of this, right? It turns out that women are quite well represented in the scientific papers in this journal, right? But they were represented very, very constantly until 2005, where suddenly the representation of women as medical subjects in scientific papers in the BMJ takes a sudden jump. Why is this? Well, coincidence or not, it turns out that that's when Fiona Godley became editor-in-chief of the BMJ, and she was the first female editor in its something 120-year history. So here you can begin to analyze directly and quantitatively the effect, we think, of women on editorial boards and so forth on actually how they are represented in science. All right, that's just purely anecdotal, right? Just kind of interesting. All right, but what we're really interested in doing is, and this is where I've spent most of our effort, is studying evolutionary biology and ecology. I mean, it's just irresistible. We're evolutionary biologists. Let's study the evolution of evolutionary biology. It's really very simple. So we got from JSTOR something like 285,000 papers, full text, right? Basically everything in ecology and evolutionary biology, back to the year dot, right? Back to 1809. I mean, before then, we're really into just a handful of German journals from 163 journals, and we filtered them for being about ecology and evolutionary biology. And you can see the explosion in the field over the course of years. There's been a 5% increase per year in the number of papers that we're talking about. And again, what we did is a topic analysis of them, and you can then study the evolution of a field in a very quantitative way. So, for instance, this is the evolution of topics associated with natural selection and adaptation. And you see here, for instance, that in the blue one, it spikes around 1900. What is that about? Well, it may suppose that this is where the Darwinian revolution is filtering through into zoology and botany, and that suddenly we're beginning to see an acceptance of Darwin, but actually it's not true. These turn out to be papers which are actually dissing Darwin. It's a whole wave of anti-Darwinian evolutionary theories in which natural selection and adaptation are being dismissed in favor of various Lamarckian and orthogenetic forces. This is all of concern to evolution, fascinating to evolutionary biologists, perhaps somewhat less so to you. But what happens then is that in the 1940s, there's a so-called evolutionary synthesis in which there's a bunch of books revive Darwin's theories along with mathematical population genetics, and you see that these things rise again. These are the classic books of the evolutionary synthesis. one of the greatest, most popular things in evolution is to build evolutionary trees. I'll speak about that again in a few minutes. And you can see the rise of these topics of how people begin, once quantitative statistical methods for building evolutionary trees arise, how they increase, and then how the data shifts, and you get new topics of molecular population genetics and phylogenetics. And of course, you can chart the single greatest revolution or change, rather, I should say, in this field, which is, of course, the rise of statistics from being negligible, in the 1940s to now. Essentially, there's no paper that isn't based upon statistical inference, and you can see the rise of Bayesian statistics as it becomes increasingly fashionable. All right, so that's just the sort of trends that you could observe in any kind of field, right? And one of the things, one of the things that we were interested in, right, was the question of evolutionary rates. So evolutionary biologists are terribly interested in evolutionary rates, and they've developed, the rate of change of some phenotype over time. Whether it's Darwin's finches that you're watching over the course of decades, or whether it's trilobite shapes that you're watching over the course of hundreds of thousands or millions of years in the fossil record. So they've developed statistics which enable you to capture that rate of change. And one of them is called a Haldane, after the famous population geneticist. And so this is just a straightforward example of taking this tool from evolutionary biology and applying it to culture. And the Haldane works like this. It's the difference between the population mean for some trait at time 2 versus time 1, divided by the standard deviation, and then the difference in time. So it's a very simple statistic, but the thing that I want you to note is that this H, this Haldane, it is specific for some time interval. So you can calculate it for, let's say, 1 year differences. So you're calculating, between, I don't know, let's say between 1960 and 1961, and then 1961 to 1962, 1962 to 63, and then you're aggregating them all in that time series to get some estimate of the rate of change for that time series. Or you could do it, right, say from 1960 to 1965, and 1960 to 65, and 61 to 66. You can do it over 5-year intervals, or 10-year intervals, or 100-year intervals, and the rate of change will differ over those, depending on which interval you use, because very small changes, very rapid changes, will tend to iron out over larger intervals, right? So anyway, just bear that in mind. People have done this, but we did it again. We just got a whole bunch of cases like those Darwin's finches, where people have studied the evolution of some trait over the course of time by actually observing them. And the classic cases in evolutionary biology and these are the most famous cases of evolution in action, are the peppered moth up here. It's a moth in Britain that evolved very dark wings as the Industrial Revolution proceeded, because they were camouflaging themselves against the soot-colored trees, and they were being predated by birds. It's a very classic case. And then they became, in 1955, when there was the Clean Air Act in Britain, they shut down all the smokestack industries, and the trees in the forest became pale again as the soot dissipated, and the moths evolved back to their gray condition. It's one of the most wonderful cases of evolutionary biology. Here's another more modern case. There are these sticklebacks, which are little fish, and you find them in they live in marine estuaries and in lakes, but it turns out that when you introduce them into lakes, they evolve really, really fast. And there's this case in Lake Loughburg, Alaska, where they lose certain features, protective features, which they need in the sea to prevent them being predated, sort of an armor skeleton, external skeleton, the prickly little fish, and they lose this very quickly in lakes. And so people have studied this, and they find that these mutations just sweep through the population in the course of a few decades. Anyway, here's the bottom line. So you can measure all these things and these evolutionary rates, these processes, in a standardized way called this Haldane. And I'm going to choose Haldane H10 over the course of intervals of 10 years, and you can get an estimate of how fast they evolve. And having done that, you can then rationally ask the question, does modern culture, evolve faster than organisms? Most people think it does. I'm not so sure, actually. I think that for the most part, modern culture evolves rather slowly. And this comes back to what I was talking about pop music. The songs change, but the music remains the same. So here, for instance, we can take a look at here's the change in frequency of molecular phylogenetics, which is a particular subfield, a topic in evolutionary biology. It's the fastest evolving one over the course of some 30 years. And this is, you're looking at the frequency of the of traits in these very fast evolving organisms, and it's all scaled to the same way. And you can see that these things are evolving much faster. And we can then get a whole bunch of data sets, be it music, and this is on the top left, that's the music data set I've already talked about. This concerns 10,000 Irish American and English novels. This is the BMJ data. And then we also have a data set about the phenotypes of cars. And here on the bottom, you see a whole bunch of different animals, which are people have studied. And we can ask, what is the distribution of the rates of evolution over the course of a decade, over the course of time intervals of decades, of these cultural traits relative to organic traits? And what we find is that in general, culture does not evolve faster than organic traits, which is rather surprising. Or at least it doesn't evolve faster than the fastest evolving organic traits. There are going to be many which evolve much slower. And there are some caveats here. There are going to be some cultural traits, tech-related traits, which do certainly evolve faster than organismal traits. And cultural traits will certainly evolve faster over very long periods of time. Bear in mind that organisms can evolve over the course of millennia or greater, even millions of years, and we just generally don't have that kind of data. The traits don't really exist for that long period of time. But what we have here is a way of looking at analyzing the rate of change of entities in a rational fashion, and we find that really culture does not evolve nearly as fast as you may suppose. And the basic reason for that is pretty much, I've alluded to it already, is that because of this equilibrium-like property that things tend to be mean reverting. Culture just is relatively conservative over long periods of time, decades at least. All right, so what is it that, so I've suggested that there are changes here. We can identify these changes, and we can ask, what is it that drives these changes? What drives culture? Well, the answer is that I think that it's some kind of selection, like process analogous to natural selection, right? At least that's the way I think about it. There are other ways of thinking about it, but this just comes naturally as a biologist, right? That certain traits are favored at particular times for some reason. We have, as it were, a world of things out there which we can select from, and we choose some of them selectively in order, when we make the things ourselves, we don't do so randomly. And that process, the reason why we select things could be due to many different, there could be many different reasons why we select things. But one of the most obvious things which we could select, reasons why we might select, and I think this is one of the major forces of evolution, of cultural evolution, is success selection. It's a very simple idea. You have, you are a postdoc, postgrad, right? And you're trying to do the coolest science that you can possibly do, right? So you go to you look in the journals, and what you see is that not all journals are made equal. There are some journals which are better than others, Nature, Science, and it is those that you tend to gravitate towards, and you sort of pick out those papers and for their techniques, and borrow their techniques and use them as inspiration. Or maybe you go to a conference and there's a plenary speaker, there's an especially interesting and dynamic speaker, there's the big guys there, right? And you tend to imitate from them, and you say, oh, well, that's where that's the thing that all the cool people are doing, and you get a sense of how this works, right? You're sort of, let's say, doing straightforward, standard phylogenetics, and you go to a conference and suddenly all the cool guys, the guys who really know, they've switched to Bayesian inference, right? Bayesian methods, and you go, yeah, that's where I need to be, right? Even if you're not entirely sure about why you're there, right? You think that's what I'm looking at. That, I suggest to you, is one of the fundamental drivers of science. It's success imitation, and not just science, but culture. So is this actually true? Can we test this hypothesis? Well, this is what I want to suggest. So this is a T-SNE map of ecology and evolutionary biology as it was between 2001 and 2010, right? And what I want to do now is go on to estimate, is to return to this question of fitness, right? So what is the fitness of a paper? Its evolutionary success. I would suggest to you is that it can be estimated by its citations. So this is for any given, so what we have is any given paper, we have the citation counts. We got this data independently of our topic analysis for 1996 to 2005, right? So this is where we're estimating how many counts a given paper gets in that period of time, and we get the average citation count, and that is just a statistic that is inspired by fitness in evolutionary biology. So now we've got the fitness of individual papers, and that means we can then ask, what is the selection acting upon individual features of those papers? And what we expect, and this is the general idea, is that selection will tend to increase the mean fitness of a population as it drives a population up what we can call a landscape consisting of combinations of genes, or in this case, particular features. And this is Sewell Wright's famous evolutionary landscape, selective landscape metaphor. And here I'm actually quantifying it by making a T-SNE map or a fitness landscape. So I showed you previously this map here, right? Now, what I'm doing is I'm going to take the coordinates of those topics on this map, and instead I'm going to just ask, what is the fitness of the traits of, what is the average fitness of the papers of those that constitute those topics at any given time between 1996 and 2005. This is the critical thing, right? So this is our fitness landscape of traits, and you can see that down here at MPG and G and M, these are very fit. The papers in this area are very fit. And what are these traits? This is molecular population genetics and genomics. So this reflects the rise of the new genomic technology in the 90s. All right, so that's our fitness landscape. And then we can ask is, in the subsequent years, and this data are completely independent, what is the change in topic frequency across this landscape? And what we find, what we might expect if success imitation is true, is that the fitness as estimated in 1996 to 2005 will predict the changes in topic frequency 2006 to 2010. And you can see that broadly speaking it does. So here, this is the change in frequency of these topics. So MPG and genomics and molecular population genetics increase. They increase much more than any other thing, and that is then predicted by the fact that this has a very that these papers have a very highly cited. So what the logic goes is that people observe that these papers are highly cited, that this is very fashionable, and then they pile increasingly into the field. And so you get more papers of the same sort. On the other hand, there are other fields, such as, let's say, straightforward mammalian biology, which have low fitness and which tend to decrease. All right, well, let's just quantify this here. If you can ask, you can estimate a selection, the force of selection on any given topic. These are all my topics over here. And then you can ask the evolutionary response in the subsequent years. And what you find is that you can largely explain the response in terms of the selection. And I suggested this is direct evidence for success selection. Over here we have genomics, which is a very fit topic, and it is one to which things change very rapidly. And there's, of course, variation in the data, the scatter, which is not explained by this regression. So take, for instance, taxonomy. Taxonomy is the classical science of, the oldest branch of evolutionary biology, really. It predates evolutionary biology. It's just about classifying things. And what we find is that over the course of, 50 years, the frequency of taxonomy just declines as people shift on to much more exciting things than just classifying beetles. However, it turns out that even though it's so unpopular, in the last few decades or so, there's been a revival in taxonomy, which tells us that there are some people who are prepared to still do kinds of science that people aren't doing. That is completely unfashionable, in which there's no hope of getting highly cited papers, but they simply do it because they love they love beetles or whatever. Okay, how are we doing for time? Yeah. Any other questions?
Yeah, so we got about 50 minutes for discussion to go, or whatever time you want to take. I got one question regarding the last couple of slides. So this is super interesting. You have the sort of, one could say, elegant situation that you have papers and you get AAA, basically everything in that sort of selection of whatever in all these journals, for example.
Yeah.
While in many cultural areas, we're in a very similar situation to the actual situation in paleontology, for example, where most of the stuff is not there anymore. And so how do we deal with, these frequency counts? How about all these topics that are where the naming game isn't solved, where they're not even talked about, they never make it to paper, stuff like that. So can you talk a little bit about the bias in this, basically, both in what's missing, and also as there may be words change over time, change their meaning over time, right? So we call it chaos now, we call it complexity, and right, stuff like that.
So you asked me to talk about bias in the data.
So you get patterns here that are based on frequency, like your fitness landscape.
Yeah,
is talking about a frequency, something that is countable, right? And so there is things which we don't see because they don't make it into these kind of things, into these journals, for example, or make it in very rarely, for example. And how do we deal with that? I know it's
the answer is I don't. I mean, if it isn't published, it ain't science, right? I mean, and we've got 163 journals. I mean, I think we've got a pretty good grip on this. There is one or two things that are missing. Nature, owned by Macmillan, owned by whoever the hell they're owned by, they don't put their stuff into JSTOR, right? So we're missing all the nature journals. We've got science in PNAS, but, well, all right. Are we missing a lot of nature? Yeah, that's going to tell it. We're missing some important papers there. But I think this is a pretty good, this is about as good as a data set gets. I mean, paleontologists, or archaeologists, what they deal with is just risible by comparison, right?
Yeah, exactly.
It's just completely hopeless. And yet they just charge into it and they kind of go, this is what the trilobites show, even if the trilobites lived, 600 million years ago.
Let me rephrase the question. So what I said at the beginning, what I meant to say was the elegant situation that this data is so incredibly.
That's why you want to get into culture, right?
Oh, really? Okay, interesting. Yeah, okay.
This is the data. The data are just amazing, right?
Okay.
With that kind of resolution. And it's even true of old data, if you choose it correctly. I mean, there's a curious thing which I'll allude to just in a minute, that cultural evolutionists, of which there's quite a few, a lot of them come from archaeology, and they use hopeless data. They like study arrowheads, which I just can't say, or really really, really weird Neolithic potsherds and stuff, where the data are about as good as they are in fossil trilobites, but they just ignore this world of digital culture that we're just absolutely flooded with, and that's what people should be studying, I think. Sorry, that's just a little rant on my part, but let me see if take some more questions. Mike Tam.
Yeah, can we get just one slide before when we have these Disney plots?
This one?
Yes. Basically, you said that the plot on the right-hand side and the plot on the left-hand side are just completely different data.
Yeah, they're independent of each other. That's important.
Independent of each other. Actually, well, here is my understanding, well, my question about it. Assume for the sake of argument, just as a null model, that people in each topic cite people in the same topic. That taxonomists cite taxonomy and genomics cite genomics. Then your fitness, more or less, reflects how fast a field is growing between 1906 and 2005. Yes, if the number of papers in this field increases, then the average number of citations, if they all cite their own ancestors, is
No, let me step in here. I think I know exactly what you're saying, because this question has come up before, and I just want you to note.
Okay.
No, let me just note that the changes in topic frequency that I'm observing are between 2006 and 2010. Right? Those are not the papers upon which I'm estimating the citation count. So they are not citing their ancestors. The citations, the fitnesses, are based upon 1996 to 2005.
Exactly.
So they're not citing their ancestors. So in other words, the two things are purely independent of each other. They're two different sets of papers, and
yes.
we're estimating what fitness is here, and we're predicting what is happening over here. And there's no necessary correlation between the two, as what I think you're implying. Is that correct?
Yes. May I
please?
Yeah, I accept that, and that's. But what I was trying to say is that your picture on the left-hand side, it sort of reflects how the field grows between 1906 and 2005.
Oh, that's true.
And the picture on the right-hand side sort of reflects how it grows.
That's exactly true.
Yeah, so it sort of tells me that there is persistence, that the fields which were growing in the 90s continue to grow.
That's true.
Yeah, okay.
That's true. But bear in mind that the left-hand side picture and is partly so what that tells you, the picture on the left is partly due to growth of the field, but is not logically necessary about the growth of the field.
It is not exclusively, it might be just popular among other people. That's true.
You know, so for instance, you can imagine that, you know, a revolutionary paper comes along and it gets really very, very, very highly cited, but it doesn't immediately spawn it doesn't immediately spawn many papers which have exactly that same topic content, right? That topic, I mean, just think of all the times in which we, let's say, cited a paper, a little bit pro forma without actually it being really about the topic of that we've actually discovered. Then it takes longer to filter through. So what you say is partly true, but that, I think, is no fundamental objection to what's going here. It's just part of the underlying dynamic, right? That makes it, but that's essentially why. But you're right in a sense that's got to be part of why you can predict the future of science from knowing the citation landscape now. it'd be interesting to know, and I haven't done this actually, to know whether you can predict it better from the fitness than from just looking at frequency changes. I don't know that. But that is, I think, the heart of your question. Mark,
can you extend the answer to, like, the system is also growing exponentially, right? Is that reflected in your data set, or is it because the journals are you restricted to journals, it doesn't grow that bad? Because the system as a whole grows exponentially.
Yeah, but you've got to remember everything is normalized here, right?
Yeah, but then still, nevertheless, even if you normalize and you say you take the fraction, 30% in something that has 10 million items and 30% in something that has 100,000 items, arguably maybe it has different stability going on, different fluctuation, like, basically in order to get to 2% in the year 2010 is much harder than to get to 2% in the year 1996. Probably because there is more people to convince in 2010. So the question is this what you're saying is that there is this insane stability going on, basically, if you think about it, even though the system is so crazy in terms of how it's growing. Like, if you behind your normalization, there's an unbelievable process going on, right? There's as many PhDs written right now than all the PhDs until I wrote my PhD, and I only wrote my PhD 10 years ago. So that is sort of something which I find kind of crazy. And so the right plot is sort of, in that sense, it's really mind-blowing that you get this kind of structure.
Yeah, I guess in a way. I mean,
sorry?
I guess. Maybe I don't have the mathematical intuition about it that you do. I mean, truth is, evolutionary biologists always work in frequency space, right? Because we're always interested in the frequency of genes. Our whole theory is revolving around this, so we just naturally tend to look at this way, and in terms of relative fitnesses. It's not, and certainly people consider, so there are some deep issues here about the definition of fitness in expanding and contracting populations, and we've got an exceptionally expanding population here. It's not one that I can tell you much about.
Yeah,
but it's an interesting question, whether the metric of fitness is appropriate. Mark Metz, you had a question?
Yeah, thank you. That's fascinating. Absolutely. I was. That's not the main question, but yeah, I wonder how it would actually vary across the fields. Like if you would take the, experimental psychology, where like whatever is relevant is like done within the last 2 to 5 years probably, and then you take the more theoretical parts of the field, for example, then there's way more citations about what happened 50 years ago on the same hand. And then when you take the fields from humanities, then you would have the same kind of thing happening. So I wonder how it would compare this, how the rate would compare across the fields. Because I guess that's not something you looked at, right?
No. No. So we haven't looked really at different fields. There's a deeper question. So there's a deeper question here about how the dynamics of exactly how this works, the selective force, is going to differ over time in any given field, and among fields, exactly in the way that you say. So, for instance, over here, I looked at not the fitness landscape 1996 to 2005. So it's a decade, and I predicted what effect that. I asked it, does that predict what happens in the next decade? That ability to predict that will change over time, as it's already well established. The half-lives of papers become shorter, so we tend to cite things in a much narrower window now than we did in the past. And the humanities will tend to cite much older things than natural sciences do. And I'm sure that computer scientists will tend to even cite even much more recent things than this. So essentially, you would have to tailor your analysis by but you need some sense of what the citation half-life of a paper is at any given time for any given data set, if this is going to work, right? If you're going to pick up success selection. But that doesn't, but that it would work, and that it's a phenomenon, I think is real, and I think it's incredibly obvious. I mean, I think it's exactly how culture works. I mean, in some ways, how can it not work this way? Think of music, right? You know, people, pop musicians, they want to make money. They want to make charts. Producers want to make money. They want to have songs in the charts. So they're at any given time they are scanning the charts and asking, well, what is that works? And they are adapting accordingly and putting that stuff into their music, which they're producing in their studios. The great thing about science is that we actually have to cite our predecessors, where most artists don't. You ask an artist who inspired this song, who are your inspirations, where did you get it from? They all say, it's the Beatles, but it's not. It's the guy over in Studio B that they just happen to walk into and listen, and they say, oh, that's pretty good. I think I'll nick that, or something that was in the charts last week, right? When you talk to any serious pop music, pop producers, this is what they will tell you, that they're continually imitating the stuff that's successful. But all that's anecdotal, and you can give a million anecdotes like that. In literature, the flood of mummy porn that resulted as a result of the huge success of 50 Shades of Grey, where publishers were just inundated and the public was inundated with variants of that sort, right? All as a result of imitation of success selection. But it's just that scientists, we can actually quantify it because we have the good habits, we hope, of actually citing the things that really matter in our papers. And that, of course, does assume that we are indeed citers, and we're not just citing stuff with a hell of it for the egos of our friends and so on and so forth, right? But we hope all that averages out. Anyway, let me just continue for a moment, and just let me wrap up. I just want to tell you, this is about a completely different project, but the logic is kind of the same. So, what evolutionary biologists like doing is one of the things that we really want to do, and I put it to you, is one of the most important things about culture, which we do not understand yet, and that is the nature of influence. In many ways, what we are talking about, we've been talking about influence all along, and influence is the thing that links previous generations to one generation to the next. It links it, as in biology, inheritance links genes link one thing to one generation to the next. What evolutionary biologists do is they build genealogies, and essentially historians, art historians, and literary critics and so on, they tend to think quite genealogically too, or at least they used to. It's rather less fashionable depending on the field, but people talk about chains of influence. Who is it that inspired Picasso to make Les Demoiselles d'Avignon, right? He got something from El Greco, he got something from Cézanne, he got something from Gauguin, and they got stuff from somewhere else. Whole books have been written about that kind of thing. Well, anyway, I flag this up that building genealogies of one sort or another is probably going to be, I think, the central enterprise, one of the central enterprises of evolution, of cultural evolution, much as it is for evolutionary biology, because when you build a genealogy, you can build it on this model-specific way and actually test processes that have shaped it. And I'm not going to quite do this, but I just want to give you a sense of how you can use culture at a big scale to build genealogies. And I've become interested in parts. Now, I spoke a few minutes ago about those archaeologists who are always studying rubbishy data sets on arrowheads and so forth. But I'm going to speak about what I think is one of the greatest art historical data sets ever, right? And this concerns ancient Greek pots. So you will be familiar with these kinds of pots. that I'm talking about. There's an example of one on the left. It's these black and red figure pots that the Greeks made between around 1000 BC and 300 BC. And why did I become interested in this? Well, very simply because the data were there. It turns out that at Oxford, there's a pot database in which all the pots in all the museums of the world, they've got something like 40,000 of them, have all been taken. There's photographs of all of them. And this is a process that's been going on since the early 20th century, but they put it all online now. And you can download this. You can download all these pots from all these museums with their images and all their metadata associated from them, when the pot was made and who they think make it, who the pot experts think made it, and so on and so forth. It is simply the largest body of art in the ancient world. And the reason I mention this is because I know that somebody here, Mila sent me a paper, I forget the exact name, who it was, but somebody sent me a paper about art. And so I just thought I got to get this, the evolution of complexity in art. And I thought I just got to get this in here. All right. So what are we interested in here? I won't go into great details, but I'm interested in shapes, right? That's the feature I'm interested in. And it just so happens because I met a mathematician called Stephen Marsland, who's from New Zealand, who says he's a shape mathematician. And he says, anybody who's been measuring shapes in the past is just wrong. We know how to do it properly. So that began a project which we've been measuring shapes. And here, this is one particular kind of little pot. It's called a pelliky. It's like a fat little amphora. And I'm going to give you just 1,000 pellikis in 15 seconds. And we've extracted the shapes from loads of individual pellikis. And this is the kind of data that we're operating with, right? We've taken them all and we've standardized them, and we've got the profiles of these things. And this has all taken quite a lot of work, I should say. But anyway, you get the idea, right? You can then look at these pellikis, these vases, and this is just one group of them, and you can get averages of them, a special kind of average called a Koch mean. Never mind what that is. It's just a special kind of thing in shape space, and you can see how they change over time. But now we're treating this in a very, very crude way, as if it's a linear, just a sort of a linear change of these things. And you can see how their shapes change over time, and you can use special kind of mathematics, which is this new fancy shape mathematics. This is the thing about it. I won't go into the details because we've just published this, but it doesn't operate in Euclidean space. It operates in Riemannian space. That's where shapes exist. What is Riemannian space? Well, high-dimensional nonlinear manifolds. If you heard about it, it's Einstein. It's a space that Einstein used to describe the structure of the universe. Well, we're basically using the same kind of mathematics to describe the shapes of pots, because that's how pots are located to each other in shape space. And you need special algorithms if you want to measure them accurately. And if you do so, then you can estimate the shortest path between any two pots. Let's say a very old pot from around 700 BC to a newer one around 300 BC, and you can estimate the path that you have to go through that. And this is basically the question. I won't go into pot history in too much detail, but suffice to say, around 1000 BC, the Greek civilization, the Aegean, suffered a catastrophic failure, like a extinction event, a dark age. And when they came out the other end, there were a relatively few number of pots that they had inherited from their pre-dark age ancestors, the Mycenaeans, the people whom Homer wrote about. And then, within 400 years, they evolved into all these other pots. So this is just a classic case of evolutionary biology, right? And what we're doing now is we are reconstructing the evolutionary tree of thousands of pots. And this is just a small set of what this pot looks like, and what you can do about this is even though the framework appears to be very different from the kinds of things that I've spoken about previously, where I haven't put things in these entities in a file, let's say songs or papers, in a phylogenetic framework. Here I am, and yet underlying this, the kinds of questions that we can ask using these new phylogenetic tools, these model-based Bayesian phylogenies, is we can infer exactly the same kinds of processes, because we can build a tree like this, assuming that it's either the traits in question that you're studying are either random walks or under stabilizing selection, or that they undergo rapid changes, revolutions at certain times, and so on and so forth. And then you can test these trees, which are models, these different evolutionary models built into these trees, against each other, and therefore you can infer the kinds of processes that we want to introduce. But now we are talking about the evolution of art in ancient times. Anyway, I don't have many results to tell you about that, but let me just give you a sense of, tell you some of the names of some of the people who've been doing this kind of stuff, and I'm very grateful to them, and I wish that they could be here to talk to you, but I thought this would be the better way. Anyway, that's all for my slides. And
nice.
We've got about half an hour.
Yes, thank you very much. This is great. Usual Zoom applause is silent. But thank you. So this was super fascinating. I have a sort of like, so one question out of curiosity and one maybe more serious question. The curiosity question. So the data set you're working with is the Beasley archive, I assume, right?
Oh yeah.
Okay. So that's nice. So now the other question is more serious is, but how about remix? Like if you have the, latent space of all possible vases, and you do this sort of like sort of shortest path thing.
Yeah.
So you make transitions that are a little bit like, sort of you go from one UFO to another UFO in the simplest way. But how about a way, so you get this binary tree that you can build and you can test, but then there is some vases, and the Greeks were sort of like partially famous for that, particularly the classic Greeks, to say, oh, if you want to come up with a really beautiful thing, like a sculpture, probably also applies to vases, you're going to take the arm of this person over there and the leg of this person.
No, it's a very, very good question. It's a very profound question. So I suggested to you that the most important unsolved problem in the evolution of culture, or I say the study of culture itself, really is the inference of influence networks. And that's essentially what we're talking about here. This is just a special kind of influence network, which assumes that there's a binary tree. Mm-hmm. Now, why is it that I think I can the question is, can I get away with building a binary, with capturing the data in this process accurately using a binary tree rather than a network? Mm-hmm. That's essentially the question. And in general, for cultural evolution, I would say no, you can't. And in many ways, if I was studying the vases in all their features, I would not be able to. So for example, if I was studying the decoration of the vases, the images, as well as the shapes, then I would certainly not be able to, because it is absolutely clear that the decoration of the vases operates independently of, evolves independently of the decoration. We have many instances where we have a given shape which is borrowed from somewhere else by the Greeks, right? I mean, there's some wonderful cases. There was this guy called Nicosthenes. He's a particular potter. We know his name. He signed his pots. He was into branding, right? In a way that nobody else was, right? And he was a totally savvy customer. He started making, a lot of these pots have been sold to the Etruscans, who put them in tombs. That's why we have so many of them, because they were all dug up in Italy, right? It's a slightly separate question why that is, but it's the Etruscans who preserved them for us. And so the Etruscans are not very good at painting, right? They just make sort of boring pots. But it's clear that they like their own shapes. So what Nicosthenes does, and it's absolutely clear, he borrows, and this is around 500, around 525 BC, he borrows one of the Etruscan shapes and he starts making them in his studio in Athens, but then he paints it and he ships it back to the Etruscans. So basically he takes something that they like, tarts it up, right, and then ships it back to them and signs it, right? So that's just that's one artist doing one particular thing where you've got a network. So if you're building decoration and shape, then you'd have to have a network. I think, although I haven't formally shown this yet, and there are techniques which you can ask how good is a binary tree, how well does it fit the data, as opposed to allowing for reticulations. I think we can get away with it in pots. I'm pretty sure we can. And the reason for that is partly also because I make it easier for myself. I chop off the handles and the lids, and That's another reason. So you make a potter makes a pot, and I've got quite into potting actually. The potter makes a pot, and then they can put candles separately on it, and they'll put handles of any sort that they want. And then what kind of handles they put on it changes over time. And they also then sometimes stick other things in bases and so forth. But we chop all that off. So basically we're just left with the body. And the body, I argue, and I think we will be able to show this statistically, right, in a model-based way, is essentially made as a unitary thing. It is therefore, that's what the potter does. So it's not very easy for him to just borrow the top half of a pot from something else and plonk it onto the bottom half of another pot and make some recombinant pot, which if you were building a phylogeny would require a reticulate, a network rather than a binary tree. But as I say, it's a special case in cultural evolution, and it is precisely that which attracted me to it, because virtually any other thing that you might do, let us say study the Western painting tradition, would require building a network very quickly as soon as you start expanding the number of traits. Is that a good answer?
Thank you, very good. I'm smiling because I'm thinking about like what my first encounter with cultural evolution happened near the Xerox machine at the State Antiquity Collection and Glyptothek in Munich, where I was working as a student. There was a curator whose name was Bert Käse, and he was, chewing tobacco, wearing boxer shorts, he was not very fashionable, but he had the haircut of Albert Einstein. And he was basically married to the Xerox copier. So you always had to stand in line and ask, can I copy something? And you had to wait for like an hour or so because he was doing 100% of his time copying vase shapes and putting them on these overview pictures in order to get an idea of like how he did it. So basically he was doing only the Xerox copier much slower. And the encounter with cultural evolution that happened, which I think is really illustrative, that's the reason I mentioned the anecdote, is at some point he opens his post that was coming in, his mail that was coming in, and he puts out a Mickey Mouse journal and starts reading Mickey Mouse and becomes like super supremely fascinated about like this week's issue. And I said, what's happening? What's so good about Mickey Mouse, right? And then he said, like, at this page up here, there's this and that ways, and there's this and that guy. So it turns out people who did drawings for Mickey Mouse were also ways specialists. And there was sort of like the silent communication going on, and a lot of ways people actually had subscriptions to Mickey Mouse. And basically, there's this sort of hidden layer of sort of cultural transmission going on. And it's like, wow, this in an ideal world, one could analyze all that, but at that point, obviously, digitization was in its infancy. But this is something which, reversely, we can also sort of, always say, like in 2 or 3 or 4 or 5 hops, you can go back all the way to Uruk, and you will find some kind of picture that is sort of relevant. But what I find really brave in what you're doing is like reconstructing these binary trees, because if you study archaeology or art history and come from that direction, we are super reluctant regarding this because basically since the 60s, there is this very, very spelled out theory that, there is multiple traits in objects and
Sure.
there is so bad preservation that we will never be able to sort of like retrace sort of the actual chumps. And there is...
Well, it depends what you're talking about. So bear in mind, there are 2 kinds of people studying pots, right?
Yeah.
Ancient Greek pots. There's an art historical tradition,
Yeah.
right? And then there are archaeologists, right? Because these things are fine art objects,
Yes,
and
of course,
treated as such. So archaeologists, they tend to be, skeptical about being able to reconstruct things and and they're alive to the deficiencies of the archaeological record. The art historians, not at all, right? They believe that they can identify individual painters. That's what Beazley did, right? They give those painters whose names we do not exist. I gave you an example of Nicosthenes. That's an exception. We know the guy's name, right? But they'll just call it the Berlin painter after a particular vase, and then they group vases stylistically around and they say, well, these are made by the Berlin painter. They will tell you when the Berlin painter lived on stylistic grounds primarily, not necessarily tied to any archaeology. They'll construct a biography for him. They'll say, these are the pots that the young Berlin painter made, and these are these when he achieved maturity and his masterfulness of his work. And over here he's becoming a doddering old fool. You can see where he's getting shaky in his lines. And then they'll construct a school for him. They'll say, and then, you know, the other painter, you know, must have studied with him, and here they're collaborating, and here you can see the influence, and they'll say, and this is the Berlin painter invented this pot, he invented this style, he invented this shape, or so on and so forth. I mean, so they're absolutely got a complete faith in the actual, what you see is what actually happened. It's remarkable. It's remarkable. Right? So it is an amazing data set, right? Even if we only got, let's say, 0.1% of the pots ever made.
I'd like to comment on that because I'm coming from both worlds. So I'm an art historian by training, and I think that one should not underestimate the power of sort of art historical analysis, which is based on polymorphic resemblance. So we're not looking at just the shape of the pot, but typically multiple arrays.
Many.
And that sort of locks objects in, sometimes in really fascinating ways. But at the same time, obviously it makes sense to have something like the shape of a pot and come up with a feature matrix, say. You know, people have done this with, like, even if you look at Jacques Bertin's matrix theory of graphics, which is sort of the introduction of the reorderable matrix into data visualization in the 1960s. The example is actually pots and rim width. So he actually looks at Merovingian artifacts doing that kind of stuff. And so there is a notion that archaeologists in that way tend to do, which is they want to diagonalize the matrix, or, you know, similar things like some kind of primitive statistical inference. But then again, you have to go out and it's like, okay, how probable is it that your watch is more similar to your father's watch than it is to your grandfather's watch? It's much more probable that you get your grandfather's watch as a present than your father's, and it's also much more probable that you want to have something different than your parents. So there may be fluctuations, and then your whole diagonalization of the matrix and everything that is like a smooth transition probably is less, you know, doesn't work as much. You have shown two examples. There was rock and roll, which had fluctuations. Yeah. There is, you know, in science you had like sort of a thing that goes up and down. I think that is a really interesting thing. We should have these kind of models of gradual change, but then we need to look at the objects, and it often turns out that graduality, while at a mean level, is something we can see more specifically. It's probably a really bad expectation, and I think that is sort of something that makes it the bipolarity of like this hitherto qualitative polymorphic approach of art historians and the quantitative approach where you look at a single feature and say, how does that evolve? The combination of the two is, I think, something that will probably happen or is already happening right now, where we get a lot of correctives where these two things come together. And I think it's brilliant to do it. Like I say, you know, this having that binary tree is sort of really cool, but one probably has to be prepared that, like, you know, sort of qualitative researcher will pick it apart, basically, isn't it?
So there's much of what I say, you said a number of different things there, and there's much of what I sort of broadly agree with, yeah? I think, you know,
yeah, of course, yeah.
But let me just say this. So I love these pot historians, art historians, right? They know their pots so well, and they love their pots so well. And they're really old school scholars, right? They publish these expensive monographs. Every 20 years, they'll publish some, you know, expensive monograph on which only 5 other pot scholars read about the, you know, about the Amasias painter, in which they consider his oeuvre, and which they consider all these pots, and they visited all these pots individually in museums around the world. It's absolutely amazing, but it's very difficult to talk to them and ask them clearly what is it that makes a pot by a given potter. right? What makes this a Berlin painter plot rather than one of the students? They never give concrete lists or data matrices by which you can objectively, anybody else can objectively identify it. If you want to do this, you want to be a pod expert, you've got to go train as a pod expert. Basically, it's almost like a religion that you've got to go sit with these people, absorb that intuitive connoisseurship, and you've got to totally drink the Kool-Aid. And generations of scholars have been drinking that Kool-Aid since Beazley himself. But what I would like to do is to be able to take that and convert it into objective data matrices in which you actually say, to make a plot, and you actually statistically infer or ask the question, does the Berlin painter actually exist, right? Statistically, as independent from those pots which are said to be made by somebody else, right? And if you did that, well, then we're all on the same page and we can begin to do science, right? And that would have to be done with these people because they do know their pots and they know the things that should matter, but they are so reluctant to deal with quantitative inference that it's actually a bit of a struggle to talk to them. So, and I say that with all, you can, but it's the younger people, right? Anyway, broadly speaking, I absolutely agree with you, but I think that's the way art history is going. It's going to be basically trying to quantify the insights, the qualitative insights of the experts. Yeah. Were there any other questions? Mike, did you have another question?
Well, first of all, thank you very much. It was really fascinating and provoked lots of ideas, what you said. And I sort of Googled a little bit, and I've seen that you put your data publicly available as, for example, for this revolutions paper and music paper. So yeah, thanks for that. Sort of, I already had some ideas. Actually, one question I wanted to ask you is: have you tried to look what happens with the diversity of topics at the point of revolution?
Yeah, we did actually. That's in the 2015 paper. We look at we studied the diversity of topics using, I think, Shannon's diversity metric. I can't remember exactly. And the bottom line is that there are some of these revolutions which is flat in diversity. Not the rap revolution, as I remember. It's the one that's really striking is the 1982 revolution in American popular music. And that is essentially the rise of synthesizers and drum machines, which just flatten the musical landscape as all genres start using synthesizers and drum machines, and everything begins to sound like flock of seagulls. I mean, it's fascinating, right? I mean, really, the musical landscape just gets flattened at that time, and then, I mean, if one had more such instances, one almost suspects that what is driving then the subsequent rapid rise of rap is just a sense among consumers that, Jesus, give us something new, right? I mean, that there's a strong desire for change, but I mean, that's merely an anecdotal speculation because we don't have enough cases of it.
What do you mean by flattening landscape? Everything becomes similar to everything?
Well, I just mean that if you just look, what I mean is that there are topics associated with synthesizers and drums and drum machines, and they become very, very prominent. And what that means is that the diversity, the relative frequencies of other topics then changes accordingly, and so the diversity metric changes. It becomes much lower. The music becomes less diverse because every song has got practically everything from country through to ballads through to whatever has got synthesizers plastered over it.
Okay.
That's what I mean. I think it's so. Yeah, I mean that's exactly what we've been studying.
Mila.
Sorry, I can't see.
Yeah. I really enjoyed your talk, and also I have a lot of ideas. But I actually, this is maybe continuation of Mike's question, or the things that you just said about, because what I have been thinking about through your presentation and the questions and discussion is that, are there any kind of research on layers, different kind of like cultural layers of evolution? I mean, kind of like my background is in cultural history, and there is of course kind of like this concept of longue durée, certain kind of like historical things that change really slowly. But then there are also kind of like there is a concept of layers of kind of like maybe some like newspaper changes in culture, so that there is all the time something happening and so on. So, and I was kind of thinking, you mentioned that there are these differences between decorations and shapes of the vases. So and I also started to think that so with your examples of music, you mentioned that there was this huge like revolution when rap was introduced, but then there are these continuous features like certain kinds of like female voice or something that are kind of like there all the time. So I'm just kind of like trying to or are there any kind of like studies on these kinds of like different layers of evolution in culture?
By layers, you mean different time frames?
Yeah, and
or that's one way to think about it.
Yeah, what I mean is maybe well, just not knowing your music data, for instance, but for instance, when you were studying this music data, did you encounter any kinds of like that there are maybe some rapid changes in, I don't know, in some style of singing, for instance, when they introduce rap and so on? But then if we look at like drum rhythm and so on, maybe there are some changes that are kind of like not changing rapidly, but maybe in kind of like in span of 20 years.
Oh yeah,
there would be these kinds of like different rhythms of change also.
Right.
It would
So
be another way of
let me
it.
just I'll try to I can answer that in two ways. Well, I can answer it in sort of formally and informally. So formally, a number of the tools that I've spoken about, or methods, such as the revolution detector, and also the Haldane rate estimator of rates of evolution, both of those are specific to a particular time interval. So you can study the rate of change over a year, which or probably you don't do less, because usually your data aren't good enough for that, or you can study it over 20 years or 50 years. Usually you can't study it more because your data aren't, we don't have data for more than 50 years, right? It's usually 20th century data, or the latter half of 20th century data that we have, right? But you can use those tools to study the rates of change or the probability of a revolution at any interval you please, and you will get different answers according to which of those you look at, precisely for the reasons you adduce, namely that there are very micro fluctuations which are happening, which are driven by one thing, and yet those things can be averaged out over a longer period of time, so that they cancel each other out, so that you can have lots of change over a short period of time, but over the long period of time, it appears to be nothing. In evolutionary biology, by the way, this is a well-known phenomenon that the rates of evolution, apparent evolution, decrease with the interval of time that you look over. There's a literature devoted to it. It's called the paradox of stasis, and it is precisely that paradox of stasis which shows that it just says that you can have lots of change over short periods of time and then averages out and you get, there's no paradox at all if you think about it. But people puzzled about this for some time. How is it that when we actually look at the Darwin's finches out there, we see them changing so much? But if we extrapolated like that, they would evolve into ostriches in a century, right? But they don't. They just remain Darwin's finches for millions of years, right? That's the paradox of stasis, yeah? All right. So, in an informal way, how can you study this? Well, one of the things that I'm doing, and this is back to pots, is that I'm studying pot evolution in the ancient pots over the course of, I don't know, call it 6 centuries or so, which we've got good data on pots. But tomorrow, as it so happens, I'm going to Greece, and I'm going to an island called Lesbos, and in Lesbos, I'm going to sit in a potter's hut, where the last traditional potter in Greece, he works in the hut next to mine. I've rented one of his pots, the hut of a dead potter, and I'm going to be sitting there observing this potter and collecting pictures of pots made over the last few decades. And I'm inspired to do so. This is all getting a little bit mad and pot the pots have just taken over. It's really, I don't know why. I never even liked pottery, but anyway, we have to live the life we've chosen. And the idea is that that's going to be sort of a micro-evolutionary study, right, of the dynamics of how living potters make pots, how his dad made pots, how his grandfather made pots, and our other potters in that community have made pots over the last century. And that highly detailed study and the dynamics we can infer from how pot shapes are inherited may help us to infer the dynamics of what happened 2,000 years ago and more over the long durée of pot evolution, which itself is not even such a long durée, bearing in mind that somehow all those pots go back to some Neolithic beaker, right? But in principle, the data are there. It's just that they're really convenient for the Beasley archive. Anyway.
So we have time for one last question, I think.
Well, it is less a question than a comment, but basically what you are saying that the longer the measurement time, the slower the average pace of evolution seems to.
Yeah, that's a very generally observed phenomenon. Yeah,
it seems it is very typical to continuum time random walks, and I would say that it's probably what you would expect from the picture of punctured evolution, because you have distribution of your times you are sticking at some equilibrium, which is essentially power law, and that will produce, if you average over different periods of time, it will produce.
So you're absolutely right. That is what you would expect, not only from a random walk, but you would expect it even more so from a mean reverting process. And if you take a look at the rate of cultural evolution paper in Nature Human Behavior, in the appendix, I think you'll see a discussion of that, in which we do some simulations on random walks and mean reverting processes and their impact upon rates of evolution precisely to it.
You need not a single random walk, but some sort of anomalous diffusion models. In some sense, Einstein-Cernik, the mean reversal thing will probably do it even more, but anomalous diffusion models can easily produce things like continuous time random walk.
Sorry, I didn't quite catch all that, but I think we agree. The paradox of stasis is not a stasis. It's not a paradox if you think clearly about it for 20 seconds, right? And the processes underpinning evolutionary processes. Yeah.
So thank you very much. I would like to re-emphasize like how I'm even more enthused that what we do is actually much closer than I thought. So there's a lot of interest which you know, in this lab in various corners by people overlaps a lot with what you're doing, and like the tremendous amount of work you have produced in this direction. I think I find it very nice that you outlined these challenges, some of which we're working on. So the polymorphic family resemblance of objects is sort of something we try to tackle with a method we have developed together with Sebastian Arnert from Cambridge, where we use compression ensembles. So we transform images in many different ways and then compress them. And then this gives us a vector of compression ratio. So we actually get this kind of matrix that you're looking for. Obviously not the object detection matrix, but visual similarity can be sort of, you know, the statement of an art historian, this looks like Caravaggio, is sort of something we can get to and have a sort of multidimensional space that we can see. And then this other thing, which ties back into the question of Mila, you know, looking over multiple timeframes, there I think one challenge that sits in front of us, probably in front of you as much as in front of us, is that not only is the frequency sort of like, you know, logarithmically distributed, but also the persistence in time. So there are certain things that exist for a very long time. Some stuff exists for medium duration, and most of the stuff sort of like is blimps and goes back out of business. So we see this in archaeological topics, for example, where over 50 years, we find a clear sort of nice straight line on a logarithmic plot of how frequent topics are that archaeologists sort of and librarians classify. So that is a really interesting thing. So the one thing that doesn't go away is sort of the logarithmic nature, the exponential growth, the kind of logarithmic fluctuation, and also, you know, the kind of weird thing that you have fashion fads and very, very long durations. As you point out, the music never changes kind of thing going on. And I think we're looking forward to a world where probably in 10, 15 years, we may have a sort of like more comprehensive theory of cultural evolution, which very much may be even better than things that we have going on in ecology and biology, because the data, as you say, is so good. And so this is very exciting, I think. I would like to add at the very end, other than a big thank you for joining us, a hint on the next Open Lab seminar. Next week, we will have Agnes Horvath, who will join us from Northwestern University, where she teaches even courses on cultural data analytics, which at the university where I went, where I was working before at UT Dallas, this was like a thing of impossibility. So this is really interesting to see that this thing is catching on. She's by training a physicist, but actually does a lot of work on cinema, online, and social media, computation, social science. So this sort of like culture where people from cultural studies, humanities, and hardcore science, or hard science, sit in a room and work together on these kind of problems is sort of something which is growing. And I'm probably looking as much forward to it as you do. And yeah, thank you very much. And I hope we meet again very soon. Thank you very much.
Thank you. Mila sent me, I think it's your paper, I forgot, I didn't scope the authors, about the complexity compression painting thing, which I'm going to take a look at because it's something which I've been thinking about for a bit, but it looks like you've done it, and that's just fantastic. So I expect me to be in touch to
Okay.
have a chat.
Thank you very much.